Hello, everyone. My name is Hafsa Hafyani, and I will present our work entitled Tell Me What Air You Breathe, I Tell You Where You Are. This work was conducted within Université Paris-Saclay. So with the rapid advances of Internet of Things, along with the widespread use of GPS and other built-in sensors, several applications have emerged to collect geodata data series. One of such applications is the new paradigm of mobile crowd sensing, which empowers volunteers to contribute data acquired by their personal sensor-enhanced mobile devices. Polyscope, which is a French project deployed in the Paris region, is a typical use case study based on mobile crowd sensing. The general objective of Polyscope is getting insights constantly on individual exposure to pollution everywhere, including indoor and outdoor, while enriching the traditional monitoring system with the collected data by the crowd. So in this presentation, I will start by introducing the context of our work, plus the problem statement and the main contributions. The formal presentation of our system is explained next, which includes multi-view learning, data segmentation, and data visualization. Some demonstration scenarios are presented next, and I will conclude my presentation and present our perspectives. So in the context of Polyscope, each participant is equipped with a sensor kit and a mobile device, which allows for the transmission of the collected measurements together with their GPS coordinates as geodata data series. The recruited participants collect air quality measurements such as particulate matters, NO2, black carbon, temperature, and humidity by the multi-sensor box. And the mobile device is used to collect GPS logs and the annotation by the participants of their activity, which is also called self-reporting. This information of self-reporting of participants' whereabouts, or as we call them, microenvironments, is very important in mobile crowd sensing. It enables insights at a higher resolution along the participants' trajectories, since air quality strongly depends on the context of the participants. And without this information, the collected measurements cannot be interpreted correctly. This is why we are trying to collect them, but it is not easy nor simple for the participant to fill them in correctly. Actually, not all the participants thoroughly annotate their microenvironment, but we made the observation that the ambient air strongly depends on the context, and so is the individual exposure to pollution. For this reason, there is a great interest of making exposure analysis context aware. Therefore, there is a great interest in segmenting the data into non-overlapping segments according to participants' microenvironment by resorting to change detection, and also in automatically detecting the context of the participant without burdening them. Also, there is a great interest to visualize the results and show to what extent the detected contexts are accurate or not compared to the declared context, and vice versa, meaning that the declared contexts are not always accurate. So in this context, and when exploring the data visually, we noticed that microenvironments preserve a certain pattern. Besides, we observe the existence of an intersensor correlation with the context. The figure on the left, for example, shows that the temperature time series preserve the same pattern in the microenvironment office. The figure on the right, for example, shows the evolution of three pollutants, which are black carbon, NO2, and particulate matters. This figure actually shows that BC and NO2 preserve the same shape and statistical features in the microenvironment score. And we know that particulate matters preserve the same pattern in the indoor microenvironment. Plus, we can observe the existence of a correlation between the dimension through the whole timeline. Also, we have made this observation that participants' context is very highly correlated with ambient air. Let's say that an abrupt change in temperature or humidity, for example, is correlated with a change in microenvironment as shown in these two figures. So in this work, we hypothesized that the multivariate time series collected by the crowd sensing campaigns not only depends on the microenvironment, but could be a proxy of it. We promote the idea of combining air quality plus mobility dimensions as predictors of the microenvironment. But the question that arises itself now is how to combine all these different aspects of the data, which are geolocation and sensors, to identify the user's context automatically, and how much can a model discriminate the observations in different microenvironments. So in this work, we propose a full-fledged implementation that can be used in real-world applications to fill the gap between data collection and context recognition using environmental data. In our case, the input is both GPS and environmental sensor data. We formulate the task of recognition of microenvironment as a multivariate time series classification. We evaluate different approaches and provide a framework dedicated to the preparation, the application, and the comparison of different machine learning algorithms for microenvironment recognition. We also include time series segmentation based on change point detection to emphasize the automatic detection of the change in the user's context. Furthermore, we develop a visualization tool that we call COMIC, Context to Home by Crowd Sensing, to fill the gap between data collection and data recognition. Now I will formally introduce our proposed system COMIC based on multi-view learning, which takes environmental data collected from different sensors and GPS as predict the user's context. COMIC consists of a graphical user interface and 4 layers, which are the declared microenvironment by the participant, the environmental data measurement over time, the detected change point, and the detected context. Our microenvironment recognition model is mainly based on multi-view learning. The holistic schema of the model is shown in this figure, which includes 6 steps, which are data collection and preparation. The multi-view learning model, which consists of training a first-level learner on the dimensions, which allows the generation of a new data set that will be used as an input for the meta-learner to produce the final classification results. Our approach is mainly based on our previous work, where we promote the idea of multi-view stacking. It consists of training a first-level learner on each view, and then training a meta-learner to combine the output of each view and enhance the global accuracy of the classification. Concretely, from a multivariate time series, we apply a first-level learner on each dimension of the time series alone. Each dimension produces a set of predicted classes with a prediction probability. We combine the predicted classes from all the dimensions and train a meta-learner on the predicted classes to learn the weight of each dimension and predict the final class. The main advantages of using this approach is separating first-level learners from the meta-learners. So we can use any desired learners as first-level and meta-learners. Also, we are preserving the properties of each data source, as we are not aggregating data from different sources. Additionally, COMIC includes another component, which consists of segmenting the multivariate time series into coherent segments. Each segment represents a microenvironment by resorting to multivariate time series change point detection. Our change point detection approach consists of applying the cumulative sum algorithm as first-level learner on each dimension separately. Each dimension generates a set of detected change points. The output is then fed to a second-level learner to learn the weight of every dimension in proportion to the performance of the individual learners using a gold set of annotated data as ground truth. The results of change point detection and the multi-view learning models constitute 2 different layers of our system functionalities. Let's now talk about the interface functionalities. Actually, the graphical user interface of COMIC is a front-end interactive interface. It provides a list of all the participants. The user is invited to choose one participant. Then the interface provides the plotted measurements with the corresponding user declared microenvironment. The user is also allowed to choose the first-level learner among a predefined learning model lists. COMIC backend then applies the classification for this participant data and shows the prediction and the predicted context for each view and for the multi-view. This visual comparison shows to what extent the declared context is accurate or not to the declared context and vice versa. The interface also illustrates the importance of multi-view approach when compared to single view approach, which is temperature in this figure, and highlights the importance of our approach vis-a-vis users' declared context, since they are not always accurate, as shown in this example, where this participant stayed outdoors for more than 2 days. Furthermore, the graphical user interface on the backend calls the detected change point based on multi-dimensional change point detection and displays the result, which consists of the exact timestamp of the change in participants' microenvironment. Compared to the baselines, we have implemented MLSTM fully connected network as well as KNN with the DTW metric classifier for the aggregated data, which are considered state-of-the-art by the time series classification community. The interface displays the detected context by KNN and MLSTM as well as the multi-view model, and allows the user to compare the results of the 3 models. The user can see visually which model is more suitable for the data and which model generates accurate predictions. Here, the multi-view model outperforms both KNN and MLSTM predictors. I will leave you with this video demonstration how comic works.
In this video, we will illustrate the user interaction with the comic interface. This graphical user interface was implemented using Python 3.6, Plotly, and Dash Frame. The real-world environmental data, which was collected in the context of Polyscope project, is used as a benchmark of the environmental crowd sensing data. This interface showed the collected air quality measurements, temperature, humidity, NO2, DC, PM 1.0, PM 2.5, PM 10, in addition to the GPS locations that are used in order to derive the speed dimension. Besides the air quality measurements, the legend shows the 5 microenvironments: home, office, indoor, outdoor, and transport, where here indoor places are closed places except the home and office, for example, restaurant and stores. Comic emphasizes 3 main scenarios. The current interface corresponds to data visualization. Here, the participant can visualize his collected data during a campaign. Each dimension is plotted in a separate graph, and the background of the graph corresponds to the microenvironments that were annotated by the user during the data collection campaign. In the top, we have these 2 drop-down boxes. Thus, we can specify the participant ID for any user to check his data, while from the second drop-down box, we can choose the first-level learner we are interested in. Comic for now offers 2 first-level learners, either KNN with DTW metric or random forest. For this scenario, we will choose random forest as the first-level learner. Also, we have the classify button, which takes us to the second scenario offered by Python. After clicking the classify button, classification and change point detection are performed over all the dimensions. The current interface shows the new plots added. For each dimension, we have the declared annotations versus the predicted ones using the first level learner. The dashed red line shows that at this time, a change point was detected, while the background shows the microenvironment detected at each time. This scenario not only compares declared versus predicted, it also shows the multi-view approach versus the baselines. For the experiments, baselines are the KNN with DTW metric and the multivariate long-short-term memory with a fully connected network, when all dimensions are present at the same time. Those baselines are compared to the multi-view approach, and the experiments have showed that multi-view approach outperforms other classifiers. Also, using multi-view, we can keep predicting the microenvironments even with the absence of some dimensions, which is not the case for other participants. For this participant, we can visualize that he had broadly annotated his data and that the multi-view approach had a high accuracy for the predictions. Moreover, we can zoom in to select a period of time so we can visualize precisely the changes at each dimension. The third scenario is applying classification and change point detection over a specific dimension. This interface provides an additional drop-down box so we can specify the dimension we are interested in. Comic allows the user to choose a specific dimension and perform the classification over this dimension, so he can compare the predictions and the declared activity and correlate it to the measurement changes in this dimension. The first graph corresponds to the declared microenvironments. The second one is the predictions of the first level learner. In our case, the first level learner is KNN with DTW metric, while the third graph corresponds to the predictions of the multi-view approach. This participant didn't have a good annotations. The first plot shows that he was in the outdoor microenvironment for more than 2 days, which is impossible. While after performing the classification, we can visualize that the predictions of the multi-view approach are more reliable than the annotations.
Okay, so in conclusion, I say microenvironment recognition is essential in mobile cloud sensing projects such as Polyscope in order to be able to analyze the individual exposure to air pollution and to relate to the context. In this work, we promote the idea of multi-view learning with stacking to detect the user context from environmental data collected from several sensors plus mobility. The major finding of our study is to confirm that air quality is a signature of microenvironment. This has been confirmed by training on a better quality dataset, which is called Record, where the accuracy reaches 98%. We also cover time series segmentation based on change point detection to demonstrate the change point in participants' context detected automatically by a multi-dimensional change point detection model. Furthermore, we developed Comic, a visualization graphical user interface to show the different recognized context and highlight the importance of multi-view learning compared to single-view learning and other baseline approaches. We have also identified several perspectives for this work. We intend to use various algorithms for the first level learner and the meta learner as multi-view learning is flexible. We are working on adding another layer of trajectory segmentation based on stop and move detection to improve the classification performance using a better quality data set, which is called, as I said, Record. And thank you very much for your attention.